All right, here we're looking at 5.4, derivatives of exponential functions. So if you remember, here's the exponential function, f of x is e to the x. So it turns out that that function is its own derivative. So that's pretty interesting, and that actually makes it really easy to differentiate exponential functions. So looking at something like number 1, the first thing I notice there is that I have a product. So I'm going to set up my derivative using the product rule. You'll remember the template looks like so. So derivative of the first times the second plus derivative of the second, well, that's e to the x times the first. And then maybe I'll simplify this. So what is it? GCF. Let's see here. I can take out an x squared e to the x. So what will that leave me with? A 3 plus an x. Okay, I can always think about if I were to distribute that through. Let's see, I'd have 3x squared e to the x, that's this, plus x cubed e to the x, that's this. So that looks correct. I'm gonna box that. Okay, what about this next one? So this looks like a chain rule problem. So derivative of the outside, 7/2 e to the x plus 1, 7/2 minus 1 is 5/2, times the derivative of the inside. Well, that would just be e to the x. I guess that's an easy one. Okay, what about number 3? Okay, so I treat this using the chain rule. So derivative of the exponential is just the exponential, but then I have to differentiate the inside. So here I'm thinking about the inside as the exponent, or I'm thinking of the exponent as the inside. So that means I have to attach here the derivative of the inside, or the derivative of the exponent, which is just 3. So 3e to the 3x. Looks like so. Okay, what about number 4? So same idea. My 4 is going to stay in front. I'm using the chain rule. So derivative of the exponential is just the exponential. But then I have to multiply by the derivative of the inner function, which is the exponent. So what is that going to be? That's going to be 6x minus 1. So then I don't know how much simplifying I want to do. Maybe distribute the 4. So 24x minus 4 e to the 3x squared minus x plus 1. Okay, number 5 looks like another product rule. Set up that template. Okay, derivative of x is just 1 times the second plus derivative of e to the negative 5x. So that's going to be e to the negative 5x times negative 5. Okay, so what do we have here? E to the negative 5x minus 5x e to the negative 5x. Factor out the GCF, e to the negative 5x, 1 minus 5x. How about for this one, should I also look at finding a second derivative? How would that look? So again, I'd be using the product rule. Okay, derivative of the first, so that'd be negative 5 e to the negative 5x times the second. Derivative of the second times the first. Should I factor out GCF? Negative 5 e to the negative 5x? something like that. Okay, number 6 looks like a quotient rule. This was my template for quotient rule, right? So it was the bottom squared, derivative of the top times the bottom, and then derivative of the bottom times the top. So that'd be e to the x minus e to the minus x. Okay, and then I have to decide about how much I might want to simplify. So let me go ahead and distribute. Let's see what that does. Okay, so e to the x times e to the x, I add the exponents, e to the 2x, and then e to the x times e to the negative x, I add the exponents, that's e to the 0, that's 1. Okay, and then let's look over here. So I'll have minus, let's see, I'll have e to the 2x minus 1. Let's leave the denominator as it is for the moment. And let's see how this turns out. So e to the 2x plus 1 minus e to the 2x plus 1 over e to the x plus e to the negative x squared. So it looks like I have 2 over e to the x plus e to the negative x squared. So it looks like that actually turns out pretty nice. Okay, what about number 7? Okay, so I use the chain rule. Derivative of the exponential is just the exponential, but then I have to multiply by the derivative of the inner function, so of the exponent. Okay. So then I'm using the quotient rule. Look like so. Okay, so what is that? Derivative of the top, 0, times the bottom. Derivative of the bottom times the top. So isn't that just negative 2 over 4x squared? So what is that? Negative 1 over x squared times the exponential? Or 1 over 2x squared. So what did I do there? See, I canceled the 2. So what's my result? The negative e to the 1 over 2x over 2x squared. And number 8. So these are all the same idea. So I see quotient rule again. Here's my template. The bottom squared. Okay, let's fill this in. So derivative of the top times the bottom. Derivative of the bottom times the top. And then see if I can simplify. I guess I'll distribute. So I've got negative e to the negative x minus e to the negative x squared minus 2x e to the negative x. Okay, I can do with that, I guess. Let's write down my denominator. I guess I can take that GCF of e to the negative x out. Maybe even a negative e to the negative x. So what I have, a 1 plus an x squared plus a 2x. Let's double check that. So if I distributed this, I'd have negative e to the negative x minus x squared e to the negative x minus 2x e to the negative x. So that looks correct. And so I think maybe I would even stop there. Okay, what else is there? So if I have f of x is e to the negative x squared, find the equation of the tangent line when x is equal to 1. Okay, so I know I can get the slope of the tangent line by finding the derivative and plugging in 1, right? So the first thing I'll need to find is f prime of x. Okay, so chain rule. So derivative of the exponential is just the exponential, then times the derivative of the exponent. There's my derivative. Let me plug in my value 1. So negative 2e to the negative 1. It's negative 2 times 1 over e, so negative 2 over e. Okay, so this is my slope at x equals 1. So then my equation looks something like y equals mx plus b. I know my slope. Remember what I have to do here. I have to get the b by plugging in the relevant point. So the x value is 1. Here I have to figure out the matching y value by evaluating the function at 1. So that's e to the negative 1. So 1 over e. Okay, now I plug those values in here. So I have 1 over e. It's negative 2 over e times 1 plus b. And then add the 2 over e. So 2 over e plus 1 over e is 3 over e. And then I go back to this guy. And I put in my b. Which was 3 over e. And so there's my equation of my tangent line. Okay, how about f of x is x squared e to the negative x? Where is the function increasing, decreasing, and find any local maxes or mins? Okay, so let me start with the derivative. It's going to be a product rule. Derivative of the first times the second. Derivative of the second times the first. Okay, should I factor out maybe x e to the negative x? I'll have a 2 minus an x. Double check that. That would be 2x e to the negative x minus x squared e to the negative x. Looks pretty good. Okay, so now to determine where this guy is increasing, decreasing, remember what I'm looking for there is the first derivative positive, or negative. Okay. So I use my first derivative test. Okay, so I make my sign chart for the first derivative. I need to fill in there the critical numbers. So let me look at that first derivative. Let me say, where is that first derivative equal to 0? Okay, so what are my solutions? So I'd have x is 0. Now e to the negative x is never equal to 0. So no solutions there. So looks to me like my critical numbers are 0 and 2. So I'm going to put those on the sign chart. And then I'm going to test. So I'm looking at my derivative. And I'm picking something, I don't know, put a big number in there, 100. Okay, well, let's see, I'd have x would be 100 positive, e to any number is positive, 2 minus 100 is negative. This would be negative. What about f prime of 1? Well, I'd have 1 is positive, the exponential is always positive, 2 minus 1 is positive. This is positive. What about negative 100? Well, x itself is negative, e to any number is positive, 2 minus negative 100 is 2 plus 100 is positive. This is negative. Okay, so then I should be able to write out my conclusion. So let's see, decreasing where the derivative is negative. Okay, so that would be negative infinity to 0, 2 to infinity, and increasing where that derivative is positive. So that would be 0 to 2. Okay, what else did this question ask? It asked about relative extrema. So let me just think about my conclusion over here for a second. So the function is decreasing from negative infinity to 0, then increasing from 0 to 2, then decreasing. So I think I can make my conclusion. I think I have a local min at 0, a local max at 2. Okay, and then I'll use the space. Let me just see what the corresponding y values would be. So remember, for that, I have to find what is f of 0 and what is f of 2. So where is my original function? Let me write that down here. That function was x squared e to the negative x. Okay, so f of 0 would be 0 times e to the 0 would be 0. F of 2 would be, let's see, 2 squared e to the negative 2, 4 over e squared. So local min at 0, 0, local max at 2, 4 over e squared.
I don't know why that makes me laugh.
So there's my conclusion there. Here's another one. Find intervals of concavity and inflection points. So remember, when I'm thinking about concavity, I'm thinking about the second derivative. So my goal will be find the second derivative. I'll start with the first, chain rule. Derivative of the exponential is the exponential derivative of the exponent. So that's what it looks like. Second derivative. -4 comes along, then I'll use my product rule. Okay, so -4 has been accounted for, so I'm looking at this unit, and I'm looking at the product here, right? So derivative of x is 1, e to the negative x squared, and then derivative of e to the negative x squared is e to the negative x squared times -2x. So -4 in front, and then what do I have there? Minus 2x squared, e to the negative x squared. Let's factor out e to the negative x squared. 1 minus 2x squared would be left. There's my second derivative. So now I'm interested in where is the second derivative 0. So if I set this expression equal to 0, let's see, I can cancel this. This guy is never 0, it's an exponential. So actually I'm only interested in where this quadratic factor is 0. Rationalize. So looks like my candidates would be plus and minus √2/2. So now I set up my sign chart. And this sign chart is for the second derivative, which is this guy. Okay, so I plug something in, maybe 0. Okay, I'm going to have -4, e to any number is positive, and then 1 minus 2 times 0 is positive. That's a negative. Okay, √2 is like 1.4 divided by 2. This is less than 1. I'll put a big number in. Okay, so I'd have -4. Exponential is always positive. I'd have 1 minus a huge number. That's negative. Negative times negative, positive. Okay, and then one more over here. Huge negative number. -4 in front. The exponential is always positive. 1 minus a huge number is negative. This is also positive. Okay, so what is my conclusion? Concave up on -infinity to -√2/2, and again √2/2 to infinity. Concave down in between -√2/2 and +√2/2. There's that. So then what about the inflection points? Well, it does change concavity. Let's see, concave up, then concave down, and then concave up again. So I do have these two inflection points. And so those are at -√2/2 and +√2/2. And so let me clean this up again. So for this part, again, I have to look at the function itself and say, okay, so what about actually evaluating the function at positive and negative root 2 over 2 to get the y values. So where was the original function? That was up here, right? Okay, so if I plug either positive or negative root 2 over 2 in the function, look what's going to happen. You see how I have the squared here? So actually, whether the input is positive or negative, when I square that quantity, it's going to be positive, right? So that would be 2 over 4, so 1/2. So actually, for positive or negative root 2 over 2, the y-coordinate is positive 2 over square root e. So there are those guys. There is my answer then. Okay, how about one more? Remember when we talked about implicit differentiation? So that was when we had a function like so, where it was not easy to say solve for y. So we just went ahead and we differentiated both sides of this. So we said, okay, the derivative of x to the 4th, well, that's just 4x cubed. The derivative of y squared is 2y, but then because y is a function of x, we had to use the chain rule. So we had to attach the dy dx. Okay, so same idea on the right side. So derivative of e to the 3y is e to the 3y times 3. But then because the right side is a function of y, we have to multiply by dy dx. So in other words, when I'm differentiating the e to the 3y with respect to x, I find, okay, the derivative of the exponential is the exponential, but then I have to find the derivative of that 3y, right? So the derivative of that is, well, just 3 times the derivative of y. Okay. And so then let me see about simplifying. Then remember, what did I do after that? I have to solve for dy dx. Okay, so maybe let me get everything with the dy dx onto one side. Everything else onto the other side. Oops. See what I've done so far. So I have this guy, I moved this guy, so then I should have on this side negative 4x cubed. Then I can factor out dy dx. 2y minus 3 e to the 3y is minus 4x cubed. Okay, and then let me divide. And I have